Hi, and welcome to the continuation video for Calculus 1, where we will discuss limits in instantaneous rate of change and how that links to the pre-calculus concepts of average rate of change and slope from our previous video. All right, so the first thing that we're going to take a look at is the tangent line problem, which is going to be a nice beginning to this chapter and also sort of a finishing touch on the chapter where we will look at the same problem again and revisit some of these same topics to kind of close out the chapter. So I'm going to kind of go off to the side here and start with just a regular Cartesian plane, and I'm going to draw any function here. Let's say maybe something that looks like that. And I'm only concerned right now with the first quadrant, so I'm not going to keep drawing it. And let's say that we identify 2 points on here. So I'll call this one x, x value of x. So this coordinate pair would be x comma f of x. And I will move over horizontally to the right h units. So this new x value over here would be x plus h, and if I find that y value or output, it would be up here. And so that coordinate pair would be x plus h comma f of x plus h. And what we learned from the previous video was I can find the slope or average rate of change between these 2 points. So let's do that now. So that is the change in y over change in x, or f of x plus h minus f of x all over x2, which was x plus h, minus x1, which we called x. And then you can probably see that I have 2 terms here in my denominator that will add to 0. So in completion, I have something that I hope looks familiar to all of you. F of x plus h minus f of x all over h. And again, this should look familiar to you. This was called the difference quotient from your previous course. And you probably studied some of its algebraic properties, which we'll do again later in the chapter. What I would like to comment on now is what this looks like graphically. And so the average rate of change would be my slope if I connected these 2 points together right here and had a constant slope from beginning to end. What would that be? And that's what that slope would look like, or that's what that, connecting those 2 points would look like. And so that would be representative of that secant line, it's called. A secant line will go through your curve at those 2 identified points, and that is where you will find your average rate of change, or the slope between those 2 points. And so if I continued, oops, that's not really a good line there, but if I continued my line throughout those 2 points, there's my secant line. Okay? All right, and so that gives me the scenario of, let's say that I leave my house and I drive to work and I stop at stop signs or red lights, maybe get on a freeway, drive a little faster, go through residential areas, drive a little slower. But if I take a look at from beginning to end, what was my average velocity or what was my average speed, it might be something like 32 miles per hour. That does not mean that I traveled 32 miles per hour the entire time, because remember, I went through some residential slower areas, I did stop at stop signs or stop lights, and then I did get on a freeway. So I was going faster and slower, but my average velocity or average speed throughout that time interval might have been something like 32 miles per hour. That would be indicative of maybe a secant line. But if I wanted to know how fast are you going at any one moment in time, so maybe right there at this x value, that is now the secant line is not necessarily the best representative line or slope for that one point. And so what we saw in our computation of number 1 from our pre-calc video that we did, this one right here where we threw the ball into the air and we calculated the various average velocities from 1 to 2, and then from 1 to 1.5, then from 1 to 1.1, 1 to 1.01, and then lastly from 1 to 1.001. What we should have found is that each one of these intervals, the x value, the starting t value for time of 1 stayed the same, but what you'll notice was the second value kept getting closer and closer to 1. So if I wanted to get a good estimate from, what is my instantaneous velocity, my velocity at one moment in time at t equals 1, I want to try to use 2 points that are as close together as possible. Now in the past, we might have thought that 1 and 2 are as close as possible. And if you're restricted to only integers or whole values, then sure, 2 is the closest number to 1. But what we actually know about mathematics is that there are an infinite number of numbers between 1 and 2 if we can use decimals, right? So if I go from 1 to 2, and then 1 to 1.5, 1 to 1.5 is much closer to 1. And then 1 to 1.1, well again, that's much closer, right, to 1. And then 1 to 1.01 and so forth. And so the idea behind this was try to get as close to 1 as possible. And you can see as you go through your different average velocities changing. It started off being negative. Right here I have -8 feet per second. Then I have 0, which we'll talk about what that means in a little bit here. Then I have +6.4, +7.84, and then lastly +7.984. So I can actually see that these are kind of leveling off at a particular value. And so the closer my second point or my second t value gets to the first t value, I get a really good approximation for that instantaneous value. Let me show you what I mean again over here to the right. So if my horizontal distance between these 2 points is something like 5 or 0.5 even, that could be really far away at times. So if I want to estimate what is my slope right at this one point x, I want my second point to be as close to that as possible. Okay, so I'm going to put my second point virtually on top of my first point, but still with your ability to see it here. And so then if I draw the slope and the line that connects those 2 points, it looks something more along that line. And because what I'm going to say is that we want h to approach, that's what that arrow means, approach 0. In other words, I'm looking at a limit, which you'll learn all of this notation here throughout the chapter, but I'm looking at the limit of this as h approaches 0. So I'm going to bring this second point in as close as possible along my curve to the first point, and then I have what's called my tangent line. Now a tangent line by definition will actually go through your curve one time and it will take the shape of it. And so if you take a look at what it actually might look like, if I have that right hand side, for example, of a function, which might mimic a parabola at this point, and I have a point right here, my tangent line might look something like so. Okay? And so it actually only goes through one time or touches my curve one time, and it's going to take the shape of my curve at that point. It doesn't, come in perpendicularly or anything like that. It's going to take the shape of it. So we'll determine, what this tangent line means and what this does for us for calculus. But what this is really doing for us right now is if I look back at that first example where we've calculated all of these average velocities, I can now try and say, okay, what is the instantaneous velocity when t equals 1? I can now try to use that information to determine what was that velocity at one moment in time, because you are going to move that second point in basically as close as possible. So if I look through my 5 options here, I have from 1 to 2, 1 to 1.5, 1 to 1.1, etc. My closest 2 points are these last two right here, from t equals 1 to t equals 1.001. Those are the two closest t values surrounding t equals 1. So I could estimate it, and again, when they say estimate, you're going to go ahead and give a pretty good estimate. Well, if that slope, if that average rate of change or average velocity was 7.984 feet per second, my estimate for that instantaneous velocity is going to be something close to 8 feet per second. And so what I can see is that, I was negative, then 0, and then positive, and I can see as I'm going through those 5 average velocities that I was actually getting closer and closer to 8. Well, I bet if you did from 1 to 1.0001, it would be even closer to 8 feet per second. Okay? And so again, an instantaneous velocity is actually what your speedometer in your car, for example, is telling you. How fast are you going right now? It's at one moment in time. And so that's why we look at this sort of tangent line problem that I've drawn over here, because again, if we want to know what is happening at this one moment in time, the only way that we know how to calculate slope is if we have 2 points. Well, if I'm trying to mimic what's going on at one point in time by using 2 points, we don't want those 2 points to be real far away, because that's not going to be a good indicator of what's happening right then and there at that one moment in time. So I just try to put it as close as possible and then use that to give a good estimate. And so we're going to take a look at this difference quotient again later on in the chapter to actually define what a derivative is for us. Now you're going to see different representations for the same concept, so I just want to go through this one more time with a little bit different language. But you're going to begin with the secant line, which means that when you look at slope, you have 2 points. Okay, so your secant line will cross through your function at 2 points. This is also average rate of change. And then as the limit, and I just want you to look at this notation right here, as the limit of your secant line, and then right below LIM or limit, it says delta x approaches 0. And that means change in x, or the h that we called it, that horizontal distance that you're moving to the right. So what happens is, as the 2 points become as close as possible, they're virtually becoming 1, but you still have them separated as 2 points, because in order to calculate slope, we need 2 points. But as they are becoming 1, your line is becoming the tangent line. And then throughout this chapter, and specifically towards the end of it, we will talk about that slope of that tangent line and what it means to be a derivative. So for now, we're just using this average rate of change to estimate our instantaneous rate of change. So we did it here. Now be careful, because sometimes the problems aren't quite as leading as this one. We specifically led you from 1 to 2, 1 to 1.5, where the second point was getting closer and closer to t equals 1, and then we specifically asked you about that instantaneous velocity at t equals 1. So just make sure that you're getting closer and closer to that input value that you want. All right. Okay, so let's take a look given this table and this table talked about the amount of full-time students PVCC had during the fall semesters from 2014 to 2019. And so we talked about why the year, right, needed to be our input. So even though it's technically on the bottom of my table, it doesn't necessarily dictate which one is the independent variable and which one is the dependent. And so I wrote out my 2 points, and we found the average rate of change from 2015 to 2017. And so what we could say is we lost approximately 118.5 students per year. Or you could also just say, if you don't like the 1/2, over those 2 years, if you're not going to look at it in terms of average rate of change, you can just look at it as what was the change. Well, over those 2 years, we lost 237 students, or we decreased in enrollment by 237 students, which averages out to approximately 118.5 students per year that we decreased. So if we had to estimate the instantaneous rate of change in 2018, I can look at my table and see where 2018 is, and I have one set of data for 2018. There were 8,115 students. But that doesn't necessarily tell me what the rate of change was in 2018. And now I don't necessarily have a function to work with. I'm limited by this data, and that's all I have to work with. So the two closest points to 2018 would be 2018 to 8,115 students to after 2018, which would be in 2019. There were 7,900 students. This is after 2018. And I could find the slope here because I don't think I had to do that in the previous problem. So I would say 7,900 minus 8,115 over 2019 minus 2018. And I'm pretty sure I decreased in enrollment every year. So let's see what that amounts to. Okay, and what I ended up with was approximately negative 215. And if we look at what that means in words, that means that I decreased by 215 students per year in 2018. But again, this was from my data after 2018. So let's take a look at what happened the year before 2018. So let's go 2017, which I had 8,447 students, to then 2018, where I had the 8,115. And let's find the slope or average rate of change between these 2 years. So 8,115 minus 8,447, 2018 minus 2017, and let's do the calculation there. Okay, so what I could say is from 2017 to 2018, so it's very important I note before 2018, right? From 2017 to 2018, I decreased by approximately 332 students per year. Again, it's a negative, so I would say decreased. And then after 2018, so for that year after it, I decreased by 215. So what did I do exactly in that moment of 2018? Well, the year before it, you had negative 332. The year after, you had negative 215. So you were somewhere in between there in 2018. So one idea might be to just average these two numbers. So our instantaneous rate of change might be add these up and divide by 2. So negative 215 plus the negative 332 and divide it by 2. Because again, it has to be somewhere in between those two values, or is most likely somewhere in between these two values. And so that would be something like about negative 273.5. And again, this is students per year, and this is in 2018. Okay. Now again, if you don't like the idea that it's negative students, let's put this in words. This is a decrease of approximately 273 or 274 students per year in 2018. Okay, so if you don't have what you would consider to be really, really close data, again, you can't find the slope just using one point. So we use the 2017 to 2018 and find the slope between those two. And we use the after, the 2018 to 2019, and found the slope between those 2 points, and then just average them together. So again, instantaneous rate of change is basically finding your slope at one point in time, which is what the calculus part allows us to do, whereas the pre-calculus kind of narrowed us to having to have 2 points to do that. The beginnings of your 2.1, you're going to find is a lot of pre-calculus ideas where then you're taking those average rates of change and estimating what your instantaneous rate of change would be, or looking at maybe what your tangent line might look at a specific point. And again, that's going to mimic what your slopes are surrounding that one point, whether it's just before it or just after it, but it'll be really, really close to it. So I hope you found this introduction video helpful, and now you can do your calculus.